Good. So I would like to talk today about some results that I obtained a series of collaborations with Nils Benedikter, with NAM, with Marcello Porta, and with Robert Seiringer. And these works have been dealt with system of fermions in certain mean field regime that I'm going to explain later. And our goal was to understand the ground state energy of this system of interacting fermions with using techniques that have been developed in the last year for the understanding of bosonic systems, and using this technique of bosonization, which allowed us to apply these bosonic techniques also in the case of fermions. So actually, I'm going to start my talk with a brief introduction to explain some ideas of bosonic Bogoliubov theory, which are going to be useful later when I'm going to speak about fermions, which is going to be the main part of my talks. So maybe before even starting, I should maybe remind you that in nature there are two different types of particles, which are known as bosons and fermions, which are described by wave function characterized by a different symmetry, but different statistics with respect to permutation of the n particle. Right? Bosonic systems are described by wave functions that are invariant with respect to permutation. So if you exchange two particles, anything like that, the wave function does not change its value, it stays the same. Fermionic systems, on the other hand, are described by wave functions that are anti-symmetric with respect to permutation of a particle. So if you permute the particles with this permutation pi, at the end you have to multiply the wave function psi with the sign of the permutation, which are denoted by sigma pi. And as we will see, these different statistics with different symmetry with respect to permutations of a particle has important consequences on the behavior and of the properties of the systems. Okay, so as I said, I'm going to start by quickly describing how to use Bogoliubov theory in bosonic mean field system to estimate or to get approximation for the ground state energy, and in this case also for the low energy excitation spectrum. Okay, so I'm going to stick to the simplest possible case. So I'm going to take n particles, n bosons, which are confined in a torus, so in a box lambda with a side length 2 pi, and imposing periodic boundary conditions, right? So that's why I'm on the torus. And the Hamilton operator of the n particle system is given by this expression here. The first part of the Hamilton operator is the kinetic energy of the n particle, just the sum of the n Laplace operator. And then there is an interaction among the particles. The interaction is a two-body interaction, so I'm summing over pairs of particles, and I have a potential V. Suppose that V is a nice positive definite, positive potential, whatever you want for this part here. It's not the point. It's nice potential, and I'm multiplying this potential energy with a factor 1 over n. This 1 over n factor makes sure. So you see, we are sitting in a box, side length order 1, so 2 pi. The potential has range of order 1, right? So essentially, this means that every particle in the system speaks with everybody else. And in order to make sure that the potential energy at the end is of the same order as the kinetic energy, so this is order n, I'm dividing here by 1 over n. And I would like to consider what happens to this Hamilton operator, in particular to the low energy spectrum of this operator in the limit of large n. So that's the question that I'm going to focus here. There are other questions which are of course relevant concerning also the time evolution, but I'm not going to discuss these questions here. Now, to explain Bogoliubov theory, it's useful to switch to a Fock space representation. So Fokker in the first talk already introduced this creations and annihilations operator. I'm going to quickly do the same here. So I'm going to describe this system of n particles on the Fock space, bosonic Fock space in this case, so Fs. So this is the direct sum over all possible small n of the symmetric component of the L2 space over lambda to the small n. Okay, on the Fock space, on the bosonic Fock space Fs, as usual, we introduce creations and annihilations operator. I'm labeling here this operator with momentum. This is convenient because we are looking at a translation invariant system, so Fourier theory is very useful here, is very convenient. So for every momentum P in Z3, so we are in this box, so momenta are discrete. We have a creation operator AP star, which create a particle with momentum P, annihilation operator AP, which annihilates a particle, and this operator satisfy the canonical commutation relations, which are these relations here. And they are defined in such a way that if you multiply AP star with AP, the resulting operator is measuring the number of particles with momentum P. Okay, so in particular, the spectrum of this combination AP star AP consists just of the natural number. This is the possible values of this number of particles operators. Good. Using this creations and annihilations operator, we can re-express the Hamilton operator in this form here. You see the first term, it's easy to guess what it is, but it's the kinetic energy. I'm counting how many particles I have with momentum P. You multiply with P squared and you sum over all possible momenta P. The total that you get, the result of this operation, is the kinetic energy of the n particles. The potential energy is a bit more complicated. First of all, the potential energy is a two-body operator. So when you translate into this second quantization language, it's going to be quartic in creations and annihilations operator. And then, of course, the potential is not is diagonal in position space, not in momentum space. So here it looks a little bit more difficult, but a simple computation to find that you have this operator here. Again, you see again this fact, this constant 1 over n in front of the potential, which has to make sure that potential and kinetic energy are both typically of the order n in this system. Okay, so good. So now we have this operator. Maybe I should stress it once again. So we are looking at a system where the particle of number of particles is conserved. And this you see it here because in each term of the Hamilton operator, you have the same numbers of creations as of an annihilations operator. So they don't change the number of particles, right? So you may think, okay, but then if the number of particles is conserved, if we look at states with always n particles, why do we bother to switch to this more complicated Fock space representation? And the reason is that as we will see in a second, bosonic systems at small temperature were characterized by this phenomenon of Bose-Einstein condensation. So there is a bunch of particles. Most of the particles are in a single one particle state with momentum 0 in this case. And once you are in the Fock space, right? So the total number of particles is conserved, but what is not conserved is the number of particles in the condensate and the number of excitations. So there can be particles jumping from the condensate to the excitations and vice versa. And that's why it is so useful to switch to this Fock space representation. Okay, so let's do it. This is the Bose-Einstein condensate, I said it, at small temperature, so at small energy. In this bosonic system, you expect that most particles are going to sit in the state with momentum P equal to 0. This means that these two operators, compared to all other creations and annihilations operators, they play a special role because they are very large, right? Remember, A star times A is the number of particles in the state with momentum 0 in this case, which we expect to be of order n. So you see, we expect both operators to be of the order square root of n, which is much bigger than the commutator of this operator, which is 1. So because of this observation, we can expect that we can replace these operators, A0 and A0 stars, essentially by numbers, right? It doesn't matter anymore that they are operators because the size is so big that the fact that they don't commute is almost irrelevant, okay? And that's what Bogoliubov did. So he took the Hamiltonian Hn, and every time you see A0 and A0 star, you replace with a factor square root of n, okay? And if you do it, you find this new operator here, right? So the first term arises from the potential energy, right? So let's go back one step. So from this operator here, if all these 4 indices are equal to 0, right, then this guy here counts as n squared. You take an n out because of this, and you get exactly this contribution here if you do it correct. Okay? Good. So there are no terms where free creations operation are equal to, or free labels of these operators are equal to 0, and one is different than 0 because you have conservation of momentum, so it's not possible. So the next contribution are contribution where you have two operators A0 under 0 star and two operators which are not equal to 0. Okay? Well, then you get this contribution. Well, this is the kinetic energy, of course, is sitting here. But then there are all these contributions here and here arising from the originally quartic potential energy, which is now reduced to quadratic because two of these operators have been replaced by factors of square root of n. Okay, good. And then there are also operators which are where you only add one factor A0 or A0 star. So we still have 1 over root n here, and we have free creations on an Nash operator on momenta different than 0. And there we have the contribution where all the indices, all the labels are different than 0. So here there is no A0 operator, so we leave it as it is, as it was. Okay, good. And now the next observation that Bogoliubov made is that, good, if I look at this Hamiltonian, it looks like cubic and quartic terms, at least formally, right, they are of smaller order compared to the rest, right? Because you see, we still have this 1 over root n or 1 over 2n factor in front, and they only contain creations and annihilations operator with label different than 0, which therefore are smaller or order 1. Okay? So Bogoliubov said, okay, let's just ignore these two factors here. If you do that, you end up with an operator which is quadratic in creations and annihilations operator. And quadratic operators are very nice because they can be diagonalized by what is called, what is now called conjugation with a Bogoliubov transformation. Okay, so a Bogoliubov transformation is a unitary map which is given by the exponential of a quadratic expression in A and A star. Okay, this operator acts very nicely on creations and annihilations operator. You can prove it easily. So if you conjugate A or A star with T, you get this kind of symplectic rotation of A and A star. You see, the conjugation of A star is a linear combination of A star and A with coefficients which are determined by the sequence tau p appearing in the transformation. Okay, so it is probably not so hard to believe that if you conjugate the full Hamiltonian, which is now quadratic only in A and A star, I'm only looking at the quadratic part, right? You will, after the conjugation, you will find something proportional to A star A, and then something proportional to A star or AA. Now, you want to choose this coefficient tau p exactly so that the part corresponding to A star or AA vanishes. Okay, and it's easy to check that you can do it. The correct, there is a simple formula for the correct choice of the tau p. If you do that, you end up after this conjugation with an expression which is just a constant here, right? Plus a sum of operators of the form A star A. Right? And for different p, this operator commute, we know exactly what is the spectrum of this guy, just a natural number. So this formula allows you to compute exactly the spectrum. Well, first of all, the ground state energy, you see it here. Right? This is an expression for the ground state energy. And then also the excited eigenvalue because they are determined by this factor. Of course, up to errors which are smaller, which arise from all these terms that we neglected to get to this quadratic and okay, but this is how Bogoliubov theory works, and for this simple mean field case, it works very well. So this what I did is just a heuristic discussion, but you can do it precisely. I mean, the first one who did it was Robert Seiringer, I think 2011. So then there were other papers. Mathieu Levin wrote a paper with Nam, Solovey, and Serpati. Napierkowski and Rezinski wrote papers about that. Many other people wrote papers about it. Also, I worked on this type of bosonic question with different type of models. But maybe now that's what I wanted to tell you about bosons. I would like now to switch to fermions, so that at the end you see how this bosonic method can also be applied to the fermionic work. Okay, so here let's switch to fermions. Let's start with a real part of this talk. So also for fermions, I'm interested in a mean field type regime. So it means I'm considering n fermions. Remember, fermions just means that they describe a wave function that are antisymmetric with respect to permutation. Okay? And then putting all the n fermions in a box or in a torus of size of order 1. For convenience, we choose 2 pi, but it doesn't matter. The important thing is it's a fixed box, right? So the density is very high. And these particles, also like in the bosonic case, they're going to interact through a potential which is leaving or characterized by the same length scale as the box. So that's what makes it a mean field regime. It means that every particle interacts with everybody else, and the interaction has to be very small. Now, there is immediately an important difference with the bosonic case. And the important difference arises if you look at the kinetic energy. Sorry. So the point is that if you have anti-symmetry, if you impose anti-symmetry, right, and you look at these particles which are all in this box of size of order 1, the kinetic energy is going to be much larger than from boson. Right? You see, the point is if you have a bosonic system, right, how do you choose a state with a small energy? Well, you take the smallest eigenvalue of the Laplacian, and well, in the previous case was just 0, and you put all particles in that same state. Of course, you cannot do it for fermions because you have to impose antisymmetry. So you're going to pose the first particle in the smallest energy, but the second one already has a little bit higher energy, and so on and so on and so on. So you have to build up what is called a Fermi sea. And if you do it and you have n particle, turns out that the kinetic energy is typically going to be of the order n to the 5 instead of order n. Okay? So in order to make sure that both parts of the Hamiltonian are of order n, we rescale the kinetic energy, multiplying it with this factor epsilon square, where we set epsilon to be n to the minus 1/3. So we think of epsilon as a semiclassical parameter, as Planck's constant. So effectively, these mean field fermions are the mean field limit is linked with a semiclassic limit where Planck constant is proportional to n to the minus 1/3 and converges to 0 as n goes to infinity. The potential energy, on the other hand, it's the same as for bosons, right? I want the potential energy to be of order n, so I have to rescale it with 1/n in front of it. Okay, so with this choice here, and this is going to be the choice that I'm going to do for the rest of this talk, I'm sure that kinetic and potential energy for these systems are typically of the order n. Good. And so maybe I should also point it out here. So we are going to assume here, there are more precise assumptions coming on, but remember that we are looking at the case where the potential is of positive type, meaning that the Fourier transform of potential is non-negative. Okay. What we are going to be interested in the rest of the talk is the ground state energy of this Hamilton operator here, which is obtained, so this is the n, by minimizing the expectation of the Hamilton operator overall anti-symmetric n particle wave function with norm equal to 1. Okay, so what can we say about this ground state? So this is a difficult problem because we have n interacting particle, but there are several simplifications. And Volker already told us this just before me about the maybe most important of this simplification, which I'm going to describe again here, which is Hartree-Fock, right? Hartree-Fock theory arises from the many-body theory if you restrict your attention to states which are given by Slater determinants. So a Slater determinant is a wave function which you can write like that, where Fi is just a orthonormal set of functions in the one particle space L2 of lambda. Okay. Well, as Volker already explains everything, so I'm going to be a little bit faster now. So Slater determinants are quasi-free states, which means they are completely characterized by their one particle reduced density, which I'm indicating here with omega. It is given by taking the partial trace of the orthogonal projection onto the wave function psi later, you multiply with n, you partial trace over n minus 1 particle. So what remains, omega, is an operator on the one particle state L2 of space L2 of lambda. And if you do the computation, it turns out that for Slater determinants, the one particle reduced density is just the orthogonal projection onto the space spanned by the n orbitals F1 to Fn. Okay? In particular, the energy of the Slater determinant can be expressed as a function of omega. And this is what happens here. And you give a name to the expression as a function of omega. It's the Hartree-Fock energy function, right? You recognize here this is the kinetic energy, this is the potential energy. So this is, right, there are two terms in the potential energy, like Fock already shown in his talk. So the first one is the direct term, right? Omega xx is the density of particles at the point x, omega yy is the density of particle y. So this is what you would get if you think of these particles as being independent, right? So how do you compute the potential energy? You count how many particles you have here, you count how many particles you have there, you take the potential of these two particles and you integrate over all possible positions of the particle. But because of this, because we impose this antisymmetry, there is also a second term, the exchange term, which appears here. Okay, so to avoid confusion with what was said before, so Fokker was focusing on the case of Coulomb system. I'm taking a potential V, which is going later, as you will see. We will suppose that it is sufficiently smooth, right? In this sense, this is a simpler version of the Hartree-Fock theory as the one that Fokker was discussing before. Okay, and once you have the Hartree-Fock function, you can define the corresponding energy by minimizing overall orthogonal projection or rank n projection, which corresponds to the determinant, or as Fokker just said before, or as Lieb proved, I don't remember when, you can also minimize overall omega between 0 and 1 instead of just looking at the orthogonal projection or at the rank n projection. Okay, so you should think of this thing here as an approximation for the many-body energy. Okay, good. But what can we say about this Hartree-Fock energy? Before looking at the relation with the many-body energy, which is the main focus of this talk, let's try to understand what can we say about this number here. Because after all, we are looking at a very simple system, right? We have a translation invariant system on this torus, mean field regime. So maybe one can say something more about this number here, and indeed we can. So to understand how and why, so let's consider first the case of non-interacting particles. So let's assume the potential to be 0, right? Well, then it's trivial, right? How do you minimize the Hartree-Fock energy? In this case, it's the same as the many-body energy. Well, you have different momental states labeled by P, right? Because since you have to impose this antisymmetry, you cannot put all particles on the same, but right, if you think that this is the P space and you have particles, you have states at all these points, then you're going to fill all these states which are inside a certain ball, right? Because that's how you minimize the kinetic energy. That's how you make the kinetic energy as small as possible. This construction is what is called the Fermi sea, and you see it here. So in this case, the zeta determinant, you put a particle on all momental state, on all plane waves, with momentum smaller than some Fermi momentum Pf. Since we need to have n state and we are in n dimension, the Fermi radius is going to be proportional to n to the 1/3. To simplify our life, we are going to assume that the shell is completely filled. Okay, so there is of course, if you are unlucky, you are going to get, if you choose the number n wrongly, in the outer shell where you have your last p states, there is going to some other p states which are empty, and we avoid the situation. We assume that the shell is completely filled. Under this assumption, it turns out that even if a potential is not equal to 0, even if you choose a potential different than 0, as long as it is positive definite and so on, the minimizer of the Hartree-Fock energy is exactly the Fermi sea. Okay, omega f does not only minimize the free energy, it's also the minimizer of the interacting, so the energy with the potential d. And so we find a closed expression for this quantity ENHF. Maybe it's not completely closed because you see to some, but anyway, it's an expression, it's explicit expression for this Hartree-Fock. As Volker already mentioned in the first talk, in the more general situation, first of all, not mean field and also not this assumption here, it was Gontier Christian Heinzel and Matteo Levin recently proved that the minimizer of the Hartree-Fock functional is not going to be the Fermi C, is not going to be translation invariant, but the energy is very close to the one of the translation invariant. It's very close to the one of the Fermi C. The difference is exponentially small, or sub-exponentially small in the number of particles n. Okay, so for us here, because of our simplification, we will have that this is equal to that. If we didn't do the simplification, they would not be the same, but the difference would be exponentially or sub-exponentially. Okay, good. So I think that's what I wanted to say about Hartree-Fock theory. So now let's come back to the many-body theory. The question that I would like to address here is how good for an approximation is Hartree-Fock theory, and what is the next order correction? Okay, so Volker told us in many situations Hartree-Fock is a good approximation for the many-body theory. It is certainly a very good approximation also here in the case that we are considering, in the cases that we're considering here. But our question is, what can we say about the next order correction, which is known as the correlation energy, right? The Hartree-Fock energy somehow is the energy that you get if you consider particles being non-interacting in a sense, right? So the next correction is due to the correlations among the particles, which are due to the interaction among the particles. That's why it's called the correlation energy. And what we can prove is the following. So this is the condition that we have to, that our potential has to satisfy. This is not satisfied in the case of a Coulomb interaction, but that's just as it is. So it's a smoother potential if you want. We still assume the potential to be positive definite. In that case, we show that the difference between the true energy and this one here, which is the Hartree-Fock energy of the Fermi C, which is exactly the same as the Hartree-Fock energy because of what I said in the previous slide, is of the order epsilon. Epsilon is n to the minus 1/3, and the constant is given by this expression here. Okay, so maybe just to stress it again, we are scaling the Hamiltonian so that this guy here and this guy here are both of order n. When you take the difference, what we prove is that the difference is to leading order of the order n to the minus 1/3, and this is the constant which comes with n to the minus 1/3. Okay, and then of course there are other corrections, but they are even smaller and we don't see them. They get erased when you take this image. Okay, some remarks. The first one, okay, and of course the proof of this result goes through an upper bound and a lower bound. The upper bound is a bit easier than the lower bound. In particular, the upper bound is true even under this weaker condition on the interaction V. And this condition, you see, if you have a Coulomb potential, you should think, well, of course, we are in this box, so there are corrections, so on, but think of V hat of K to be 1/K squared. So V square is 1/K to the 4, so this is barely divergent. Okay, but anything smoother than a Coulomb potential would satisfy this estimate here.
I mean, there is a question for you.
Is there a question? Sorry, I didn't see.
Yeah, can you hear me?
Yes.
Yeah, so the 1 minus lambda arctangent thing must be some sort of a polarizability.
Sorry, the what?
Must be some sort of a polarizability, right? Since you said that it agrees with the RPA calculation, that 1 minus lambda arctangent something, that must come from polarizability.
You're looking at this thing here.
That's right.
So that's the explicit expression which comes out of a computation which is based on this Bogoliubov theory that I showed you before. So in the fermionic setting, this plays the role of this strange Bogoliubov sum that you have here, in a sense. Okay, but then we can see it later. I don't know if you have a better interpretation for it. I don't.
No. I mean, just by your remark too, that agrees with the RPA calculation, it should mean that the term there should really be a polarizability, things like that. My question is why that thing looks so simple. That looks, rather simple to me. So
okay.
There's some insight why it's just like such a universal term that doesn't even depend on V or something.
Well, the V is here. V is
No,
there.
V, that separable V is expected. It's supposed to be V times something. But the thing that is being multiplied is so simple. Just wonder whether there's some.
I don't know if I understand. If you take this log and you expand it, the linear term in V is cancelled by this guy here. It's going to be quadratic in V. So you're going to see a sum of k V hat of k squared. So this means if you really look at the Coulomb case, which was what physicists were looking in the old days, so this formula was somehow predicted in some other form by Gell-Mann and Brueckner, but it was predicted for the Coulomb case. In the Coulomb case, the correlation energy would be not of order epsilon as is written here, but epsilon times log epsilon. So there is an extra logarithmic correction because k times v squared is not convergent also for the Coulomb. But why you get this exact constant? For me, comes out from this Bogoliubov theory, or from this random phase approximation, which is essentially the name that was used in the physics literature for this approach. But I don't have an explanation why it looks like that. Maybe let me go on, and then we can see later if it comes out from the computation. If you see a better interpretation. Okay, so the other remarks that I wanted to do, well, one as I already did. So this was predicted in the physics literature actually for Coulomb system with non-rigorous approach, which is known as this random phase approximation. The other remark I wanted to do is that this result here, you see it's joined with Niels, with Marcello, and with Robert. This is the last step, and previously we had a different actually the same result, but under much stronger condition on the potential, proven together with Niels and also Nam with Marcello and with Robert. And also the other remark is that at the same time as we came out with this final version of the result, Nam together with Christian Hansel and their student, I think Martin Christensen, came out with a different proof, exactly the same result, the same conditions. Well, maybe I should not say exactly the same result. Maybe we formulated a little bit less, but the same condition, a little bit differently, but we have the same conditions we have. Their approach is a little bit different. If I will have time later, I will explain what's the main differences. Okay, let me now switch to some elements of the proof of these results. Now I still have 15 minutes, is it right? Okay, let's go on. Good. So also in this case, like we did for the bosons for the bosons at the beginning, let's switch to a Fock space representation. So I introduced this time, of course, the fermionic Fock space, summing over all antisymmetric subspaces of the L2 spaces. On the fermionic Fock spaces, we can introduce creations and annihilations operator A and A star, exactly like for boson, but now this operator satisfies canonical anti-commutation relation. So this parenthesis here it means that you take A times A star plus A star times A. Also in this case here, we can express the Hamilton operator in terms of this A and A star, and this is what you get down here. Okay, so now remember the first thing that we did in the bosonic case was essentially to remove this Bose-Einstein condensate. Of course, now we don't have a Bose-Einstein condensate, but now we have this later determinant. We have the Fermi C, right? So what we would like to do, we would like to factor out this later determinant, this Fermi C, so that we can focus on its excitations. Okay, and to do that, we find a unitary operator R. This is a fermionic Bogoliubov transformation sense with the following property. So R maps the vacuum onto the Fermi C, so onto the state where you have a particle for all momenta P smaller than the Fermi momentum PF. And this important property here, that when you conjugate a creations operator, you either get again the creation operator if your P is bigger than Fermi momentum, and you switch to an annihilations operator if P is smaller than a Fermi momentum. So the idea here is that you think of this is the state that we have, is this Fermi C here, right? All particles occupied states within this Fermi C. Every state outside is free, is non-occupied. So now if you want to create an excitation of this guy, there are two possibilities. You can either create a particle, an extra particle out here. So then in this case, the AP star is still an AP star. Or you can create an excitation by creating a hole in the Slater determinant, okay? And how do you do that? Well, you have to see here. That's why when you conjugate inside the Slater determinant, your creations operator turns into an annihilations operator, because to create an excitation inside the determinant, you need to create a hole, essentially. Good. So that's what this operator, this unitary operator here allows us to switch to a new representation of a system where the vacuum describes the Fermi sea, okay? And the excitations of this vacuum are just excitation of the Slater determinant. Good. Now, maybe this remark here, of course, you see, initially we have an n particle space. Now we switch to the, applying the R, we switch to this Fock space. To be more precise, the only sector of a Fock space which is relevant if you want to look at n particle system is the state where the number of holes is the same as the number of particles, to be more precise, but maybe it's just a detail. Let's go on. Good. Once you introduce this R here, then of course you would like to understand also the energy of the system in terms of these excitations. So you conjugate the Hamilton operator with the R. Okay, so here is what happens if you do it with the kinetic energy, right? So here we have to compute the action of the R on the AP star AP. We have to distinguish two cases, P small and P large. If P is small, right, you remember the action of the R is to switch A star to A and A to A star. If you are outside the determinant, nothing changes, okay? Good, so now you have this term here. You want to put it back in normal order. So you want to move A star in front of the A. If you do it, you can, using the canonical anti-commutation relation, you get an extra contribution, which is exactly the energy, the kinetic energy of a Fermi sea, okay? And apart this kinetic energy of a Fermi sea, what is left is this operator H0, which is the energy of the excitations of the Slater, the excitations of the Fermi sea. And that's how you measure the kinetic energy of this excitation, right? So you measure, this is the normal energy, if you want, normal in the sense before the transformation, but now you have to compare it with the energy on the Fermi sea. You only count the energy difference from the Fermi sea. That's how much an excitation costs. Creating an excitation with momentum P, that's the cost of it, okay? In terms of kinetic energy, of course. Okay, so now this is very easy for the kinetic energy. You want to do the same also for the potential energy, and now it's a little bit less easy because for each one of these labels, we should distinguish, is it bigger or is it smaller than the Fermi momentum? You do, there are a lot of terms, but fortunately, it turns out, well, there is a constant here, which, by the way, is just the potential energy of the Slater determinant of the Fermi sea. And then there are three contributions which are relevant and all other contributions which are small, at least on states with few excitation, okay? And let's look at these three relevant contributions. I wrote them here, so there's these three here. And what they have in common is that they can easily be expressed in terms of a new field operator B star R or BR, so B and B star again. What is B? What is B star? So these are, you see, you multiply two creations operator in the fermionic language, and you sum over all possible P's. And what the important thing of these two fermionic operators is one, so the P creates a hole because P is smaller than the Fermi momentum. The second one creates a particle because you are outside the Fermi sea. Okay, so this operator creates particle hole pair. Okay, distributed around the Fermi sphere, if you want, because I'm summing over all the P's. Okay, and the important observation now, and that's how when I come back to the bosonic theory was talking about at the beginning, is that this new field operator, now they are quadratic in the fermionic operator, so they at least approximately satisfy again some canonical commutation. Okay, so you see, you can interpret the potential energy of this excitation in terms of bosonic creations and annihilations operator, but better said, in terms of approximately bosonic operator. Okay, So that's the summing up what we have. The new Hamiltonian is a constant, which is just the energy of the slated determinant, the energy of the Fermi sphere. And then there are these two main terms here, the kinetic and the potential terms, and then correct. Okay? So now we are very happy because the potential term is written as a quadratic form in creation in this bosonic or almost bosonic operators, and we know how to diagonalize them. So the only question which remains is the kinetic energy. The kinetic energy is still expressed in terms of the A operator. So how can we switch to the B? Well, let's try to apply the kinetic energy operator on an excitation created by this B operator, right? So you do it here. Now you remember H0 is given here. So you have AP star AP. Of course, you have a contribution from Q cross R and a contribution from Q. One is a particle, one is a whole, so they come with different sign. So there is some cancellation. The main term, the Q square term cancel, but you still have a term Q times R, which does not cannot be taken out of the sum, right? So it's not given. The result is not just a constant depending on R times the same state. So these states are not eigenstates of the kinetic energy operator. In other words, the kinetic energy operator cannot be written as a quadratic operator in terms of this P and B star operator. Okay, so we have to do something else, and that's the whole point. That's our main idea. We do so by dividing the Fermi sea into patches. Okay, so we divide. So you see, we localize. Well, first, we divide into patches. So the patches are sort of small, but also not too small. I'll come back in a second to that. Once you divide this sphere into M patches, then you can define new bosonic modes, which are now localized into these patches. We don't sum over the whole sphere. We only sum in the vicinity of some of these red points, which are the center of the patch. Okay, and what is the advantage of this new operator? Well, the advantage is when you apply the kinetic energy operator, you do the same computation as before, but now the Q, right, it's a point here on the patch, so we can approximate it with a red point, with a fixed red point, which allows us to take it out from the sum. Okay, so if you define it, so you need two conditions, right, to define. First of all, you need the patches to be small enough to be able to make this approximation here. On the other hand, it has to be big enough because it has to contain sufficiently many fermionic modes so that their average still behaves like a boson. Okay, the fact that the B behaves like a boson is because I'm averaging over many fermions. And if you have too few fermions, this is not true anymore. Okay, well, we have to optimize the parameters, of course, but we do. And with this choice, we obtain an operator which H0, which is quadratic in B and B star, so that now the full Hamiltonian, the full excitation Hamiltonian is a constant plus something which is quadratic in B and B star, in this almost bosonic operator. So what is left to do is to just diagonalize these almost bosonic quadratic expressions using the same bosonic Bogoliubov transformation that we're using for the bosons at the beginning of the talk. Okay, of course, now expressed in terms of this B's operator, right? So since these are our Bogoliubov transformation, you see, they're quadratic in the B's operator now. So of course, these B's are not exactly bosonic, so these do not behave exactly like bosonic Bogoliubov transformation, but out to small errors, which I neglected here, you still get the same action as for the bosonic Bogoliubov transformation. And if you choose this parameter K here in the correct way, what you get is that this thing here is a constant. This is the constant plus quadratic diagonal contribution, which is positive, right? So the ground state energy, how do you get it? Well, it's already written. You just have to evaluate this expression here. And that's what we did here. And it turns out that this trace, if you do the computation, the trace of this combination of these operators E, D, and W is given to leading order by this log here. So I forgot, no, the epsilon is here. You see that this is the order of the operator. And that's how we prove our main result. I think that's, yes, well, I think this is a good point to stop. Thank you very much for your attention. Very pleasure.